Hi, this is Mark Weitzman. Welcome back to my channel, my YouTube channel, Want to Be a Theoretical Physicist. And first off, I'd like to wish everybody holidays are just about over here in the U.S. A happy holiday season and a happy new year for the coming year. So I just want to summarize what I've been doing this last week in physics. Not that much, but so sorry. So first thing I've done is continued with Coleman's lectures. And it really is amazing. I've gotten through chapter 35 now, which is sort of includes everything on QED and both the path integral approach and the canonical quantization approach. And what I find amazing is that for the first time I really understood everything about the Hamiltonian approach and what variables are independent and what aren't and how to integrate out variables. All these things, Coleman sort of does it in a very clear way, much clearer than almost every other book that I've gone through. I've gone through a lot. So one thing that I learned, which I hadn't seen before, is after computing after Coleman computes the magnetic moment, the famous calculation of the electron, Schwinger's calculation, was the first one who did it. The correction is like alpha over 2 pi. Alpha is about 1 over 137. So this gives you the G factor of the electron. G is about 2, and then there's this correction. And every QFT book does this calculation. It's not a it's a long calculation. It's not that difficult, but to get the actual numbers, it's a long calculation. But he then has a chapter where he discusses corrections, like fourth order and sixth order and so on. And he does things that I never even knew. For instance, I was always wondering, why is it different between the muon and the electron? And Coleman shows, a fourth order, the main fourth order difference. There are a lot of graphs, but this is the difference for electron and muon. We have this diagram. I'm drawing them like Coleman draws them. Everything goes from right to left. And so without this bubble here, it would be the usual second order, and we'd get back to the alpha over 2 pi. Now, what I never understood was why it makes such a big difference. And so here's an example. Let's say you're calculating the magnetic moment for the electron. And then you have and comparing it with the muon. Say we have a muon here. Well, if this is an electron, in the bubble, in the loop, and this is a muon in the loop, it's clear we're going to get the same thing. But there's also the possibility that you can get, instead of an electron, maybe you have a muon in that loop. You have an electron here in the loop. Now it's different because the heavier the particle, the less the contribution, the less the correction. A muon is, I can't remember what it is. It's like 200 and more than about 200 times an electron. I should know this. It's either like 135 or 200, something. So when this is a muon going around here, it's going to be much less effective than this. This is going to be much larger contribution. So it's simple things like this that Coleman explains so clearly. And that's why I really like the book. The next thing that I did was I decided I wanted to read Hatfield's QFT book up to chapter 10, I believe. And I'm sorry, up to chapter, let's just say through sometimes it works and sometimes it doesn't. Through chapter 9. Now, as I've mentioned before, Hatfield's is a very interesting book. It's quantum field theory of point particles and strings. And 2/3 is QFT, traditional, and 1/3 is strings. Very elementary introduction to strings. Now the thing about Hatfield's book is that it's not a good book to learn from. If you haven't read a QFT book before this, you won't understand most of it. So it's not good to learn from. But it is great to review. And especially in chapters 7 and 8, it's like a lightning fast. I know that's not spelled right. Okay. Try this. Lightning fast review. And the thing I like, it really reminds you of all this stuff. Like if you do he sort of follows in this part of the book. There's two main methods in quantum field theory. There's the canonical quantization. It has its uses. It was the first one. It's old-fashioned. Then there's the more modern path integral. But there's also another which almost no book covers, which is sort of like the Schrodinger functional. I'll call it wave functional approach. I haven't seen this covered anywhere. And it's interesting. If in case you're ever wondering, sometimes a student will ask me, he says, I don't understand. In quantum mechanics, we have the wave function psi, and we take the absolute square to get the probability. What's the corresponding thing in quantum field theory? We don't seem to have a wave function in quantum field theory. We have states and we have operators and we have matrix elements, but we don't seem to have the same wave function thing. And here is sort of how you do it, because you have a field. So basically now you're looking for the amplitude, that the whole space-time field of whatever you're doing, let's say QED, has a certain configuration, and you want to know the transition to another configuration. Anyway, it's very interesting. And but I went through the part on canonical quantization, and it's just amazing all the things that you have to do, like the Dyson formula. One of these, like the basic perturbation approach, time ordered of, exponentials of the interaction period integral. Time ordering is what makes this really interesting. And then you have like Green's functions, which is, time ordered, ends up being, you get this wonderful formula. Vn xn e to the minus exp. This whole thing is time ordered. Vacuum expectation values. And then you have the bubbles. Same integral as there. So you have these formulas. Then you have the spectral theorems, spectral identities, things like, I'm not going to define everything. I'm not trying to teach you anything here. I'm just trying to show you how, like, there's so many aspects, time ordering and normal ordering and all the things that go into this. Then you have, LSC reduction, which goes from these green functions and everything to get things that matrix elements and everything. Then you have Wick's theorem. And then you have like the combinatorics, which lead to the Feynman diagrams. And then you have things like the cross-set ward identity for QED. And then you have then you have to relate it to cross sections. You got to use trace technology. Things like the trace of P/Q/ equal to 4 P dot Q and the trace of P1 slash P2 slash P3 slash P4 slash is equal to, like, hope I remember this right, 4 P1 dot P2 minus 4 P1 dot P3. Okay, I left out a few things. Like P1 dot P2, P3 dot P4 minus 4 P1 dot P3, P2 dot P4 plus 4 P1 dot P4, P2 dot P3, all of these things. You have things like you have to interpret the square of delta functions. And it's just a lot of work to get the final cross section and everything. And I still recommend today, even though it's like 60 years old, the book by Volume 1, Borkin and Drell, Relativistic Quantum Mechanics, because it has an excellent treatment of the propagator. Here we go again. Something I don't understand why it's doing that to me. I guess I'm going to have to reboot. Square of delta functions. Then I still recommend relativistic quantum mechanics for the propagator. And Feynman diagrams. It goes through every detail of calculating these things, and it calculates a lot of classic things. So you have all these things, and I didn't even mention before, whenever you have like QED, you're going to have all kinds of gauge problems, gauge choices, and a lot of interesting things from there. So, QFT is a lot of fun, and it's just very involved and everything. And I'm a definite believer in lots of books. Just leads to like synergies. I was reading in Hatfield, he talked about the tadpole diagram. But in the context of 5-4, something like this. And I hadn't heard that term except in, Sudnecki. He said they all vanish and you don't have to worry about them. Hatfield said, and first I was skeptical, and then I remembered Sudnecki's argument. He does 5-3. So here the tadpole is, let me think how to do this with 3 lines. So the tadpole here is something like this. A little different. And I remembered this argument, but I hadn't seen it in this context. So, a lot of times you get synergies, and one book is clear on one thing, and another book isn't so clear. So, anyway, that's my what I did this last week, and I want to continue on with Hatfield, particularly to do the path integral and the Schrodinger functional approach. He's got some real nice chapters on these things. And once again, I hope everybody has a happy new year. I didn't accomplish nearly as much this year. I had a rough year in the financial markets. I had a rough year in physics. I didn't accomplish nearly as much as I wanted to. I made the mistake of taking some MOOCs that I probably shouldn't have taken, and they took a lot of time. And programming in Python, I spent a lot of time this year, and I didn't accomplish as much as I want to. But, next year's hopefully a better year. And slowly I'm trying to reduce my book log and make more videos and, build up the channel. I think right now there's about 3,300 subscribers on my YouTube channel. That doesn't really mean much. I don't know how many are active. But, if there's anything that you really want, I know some people really want me to get into to do the group theory. And now that I'm at the group theory part of Coleman, I may, this is like Coleman spends a lot of time on SU3. I may restart these videos. And I've had a couple of people ask me about self-study and physics and how to do it, and I have the whole playlist on textbooks and everything. And you just have to find your way. There's enough stuff online. There's all kinds of sites. And on my Piazza thing, I have a lot of recommendations and everything. So everybody has to find their own way on this kind of thing. And, my goal is simple. It's to get the knowledge, of a probably like a third year graduate student. I don't think I'm ever going to do any research or, I'm never going to go back to school and try and get a PhD or anything like that. I even talked to a couple of years ago, I was emailing with a very prominent physicist. I won't mention his name, but I mentioned something about, getting a PhD and this and that. And he said, "What?" And he just emailed me back. He said, "Why would you want to put up with all the nonsense involved in getting a PhD in theoretical physics when you can just continue studying it at your leisure at home?" And I kind of said he's right. I don't need. I mean, it's nice to have the letters after your name. Of course, I already have I have law degrees. I have masters in physics. I've got enough titles in my life, so it doesn't mean anything when you're like 66 years old. Anyway, Happy New Year, everybody. I'll see you next time. Bye-bye.